You are radioactive. Not only are you radioactive, but you're also producing antimatter. Yes, that's right. Every second of every day, no matter what you're doing, you're producing antimatter. Let's find out some more, shall we? I produce a new science video each week. If you enjoy these videos, then please don't forget to subscribe. Right, on with the video. An atom consists of a nucleus which contains protons and neutrons, and orbiting the nucleus are electrons. The number of protons in the nucleus is the same as the number of electrons orbiting the nucleus. The number of neutrons in the nucleus is quite often similar to the number of protons, but it doesn't have to be. What makes different elements different is the number of protons and electrons in each atom. For instance, an atom of carbon has 6 protons in the nucleus, and there are also 6 electrons in an atom of carbon. That's what makes it carbon. If it had 7 protons in the nucleus and therefore 7 electrons orbiting, it wouldn't be carbon, it would in fact be nitrogen. That's what makes the different elements different. In nature there are often different isotopes of the same element. This is different types of the same element, really. Now, we said that atoms of the same element have to have the same number of protons and electrons, but the number of neutrons that they have can be different. Different isotopes, therefore, are atoms of the same element, so they have the same number of protons and electrons, but that have different numbers of neutrons. Quite often these different isotopes are quite stable and sit happily doing nothing. Sometimes, however, some of these isotopes are unstable. In other words, the nucleus is unstable. These isotopes will decay, in other words they'll lose particles, in order to try and become stable. And this is what we know as radioactive decay. There are a number of different types of radioactive decay, but I'll explain each as we get to them. A certain percentage of particular elements is made from these unstable atoms. And since we're made from atoms, and a certain percentage of our atoms are these unstable ones. But which ones in particular? As I've already mentioned, carbon has 6 protons in its nucleus. The majority of atoms of carbon also have 6 neutrons in the nucleus as well, and this is a stable form of carbon and is called carbon-12. There are 2 other forms of carbon. Carbon-13, which is also stable and has got 1 extra neutron, and also carbon-14. This has got 2 extra neutrons in the nucleus and is unstable. Our bodies contain a lot of carbon, and even though carbon-14 is very rare, only about 1 atom of carbon per trillion atoms of carbon is actually carbon-14, an average 75 kilogram person will still have about 680 trillion atoms of carbon-14 in their body at any one time, with about 2,700 of these atoms decaying and giving off radiation per second. There's even a unit for this called a becquerel, 1 becquerel being 1 atom decaying per second. Carbon-14 decays by what's called beta emission. Strictly speaking, it's beta in minus emission, but don't worry about that. During each radioactive emission, one of the neutrons in the nucleus decays into a proton, an electron, and an antineutrino. This turns the atom into actually an atom of nitrogen, because it's gained a proton. And the electron and the antineutrino are ejected. Neutrinos are virtually massless particles that don't really interact with matter at all. In fact, every second there are billions of neutrinos produced by the sun passing through our bodies. The antineutrino is the antimatter version of a neutrino, and you're producing about 2,700 of these every second. In other words, 2,700 becquerels. Okay, so that's one kind of antimatter that you're producing all the time, but there is more. One of the other major sources of radiation in your body is potassium. There is a radioactive isotope of potassium called potassium-40. Even though our bodies contain much less potassium than they do carbon, potassium-40 is a relatively common isotope of potassium, accounting for 0.012% of all the potassium in our food and therefore in our bodies. Potassium-40 usually decays to calcium-40 by beta radiation, producing again an electron and our friend the antineutrino. However, in 0.001% of potassium-40 decays, it happens by the potassium emitting a neutrino and a positron. This positron is the antimatter equivalent of an electron. In addition, about 10% of the radioactive decays by potassium. It does so by capturing an electron, turning it into argon-40, and in doing this it also emits a neutrino and a gamma ray. Gamma rays are high-energy electromagnetic waves. The electromagnetic spectrum consists of waves of varying wavelengths. Some of these are generally safe, including visible light and radio waves. Others are very unsafe, and these include X-rays and gamma rays. These are unsafe because these frequencies of the electromagnetic spectrum are very high energy and are capable of damaging the chemicals that make up your body. Most importantly, they can damage the DNA in your cells, leading either to cell death or cancer. Radioactive potassium in our bodies is responsible for about 5,000 becquerels of radiation. In other words, 5,000 atoms decaying per second. This results in the production of about 4,500 electrons, 4,500 antineutrinos per second, and about 500 gamma rays. You'll also be producing about 3 positrons per minute. The positron is the antimatter version of an electron and has a positive charge. There are other radioactive elements in our bodies, some of them remnants of nuclear tests that were carried out during the Cold War. However, they contribute a very small amount to the overall levels of radiation that we produce. So let's total this up, shall we? 2,700 becquerels of carbon decay, accounting for the production of 2,700 electrons and 2,700 antineutrinos. Also 5,000 becquerels of potassium decay, accounting for the production of 4,500 electrons, 4,500 antineutrinos, 500 gamma rays, 500 neutrinos per second, as well as 3 positrons per minute. Most of these radioactive emissions will never leave your body. Very few of the electrons will make it all the way to your surface and then out into the environment. The same for the positrons. The neutrinos and antineutrinos will make their way out of your body, as these particles pretty much don't interact with anything. However, the roughly 7,000 antineutrinos that you are producing per second will be dwarfed by the neutrinos coming from the Sun. These total 65 billion neutrinos per square centimetre of your body per second. And before you start panicking that you're radioactive, don't worry, we all are, and it's completely natural. Everything around us is slightly radioactive, and the radiation that you produce accounts for only about 10% of the natural dose of radiation that we receive each year. Okay, so that's all for now, and until next time, thank you very much for watching.